My name is Junji. I'm from Missouri University of Science and Technology. I'm here to present our research work of the pressure fluctuations induced by supersonic turbulent boundary layers. First, I want to thank my advisor, also the PR of this project, Dr. Lian Duang, for supporting me here. Also, I want to thank our former group members, Dr. Chao Zhang, my critic, and our point of contact at Blue Water, Dr. Jahar Kwak. So we use Blue Water to study the pressure fluctuations induced by these hypersonic turbulent boundary layers. In theoretical significance, we know the high vorticity regions is usually related to the low pressure areas. So a better understanding in the pressure fluctuations would help us get a better ideas of the vorticity dynamics in boundary layers. And also, the pressure fluctuations is important as it appears in the pressure strain term, which redistributes the turbulence among different components of the fluctuating pressure velocity. So the pressure strain term is known as one of the major issues in the Reynolds stress closure. And in terms of the engineering applications on a hypersonic vertical surface, the wall pressure fluctuations will induce the vibrational loading and causing the damage of structure. And also in conventional high-speed these wind tunnels, the free stream pressure fluctuations induced by the high-speed turbulent boundary layers is largely responsible for the background noise. This is typical hypersonic wind tunnels. We can see the acoustic radiations coming from the turbulent boundary layers, and it is traveling into the test section. And these free stream acoustic disturbances will affect the experimental measurements, such as the laminar to turbulent transition, and making it less comparable with the free flight tests. So a better understanding in these pressure fluctuations would help us extrapolate the data we obtain in conventional wind tunnel to the free flight conditions. In terms of the pressure fluctuation study, however, we only have limited data. The current theory cannot predict the detailed pressure spectrum, and for the experimental data, it is difficult to obtain in supersonic and hypersonic flow. Also, the spatial and temporal resolutions has limited these measurements. For the current numerical data, the previous simulation mostly focused on the low-speed turbulent boundary layers and the pressure fluctuations on the wall. Therefore, we try to fill in a gap that our simulation will resolve not only the turbulent boundary layers, but also the acoustic radiations in the free stream. The current project will focus on two different configurations. The first one is the single flat wall, and the second one is the axisymmetric nozzle. So this one will be used to study the axisymmetric effect on the turbulent boundary layers and their acoustic radiations. So why blue water? As I mentioned just now, our simulation will resolve both the small turbulence scales on the wall and acoustic fields in the free stream. Therefore, extremely fine mesh is required to resolve both the small scales on the wall and acoustic scales in the free stream. And at the same time, the domain size has to be large enough to accommodate these large-scale coherent structures. And in order to study the low frequency behaviors of the pressure spectrum, a very large number of time steps is required. Production run usually requires 1,000 computer nodes, and they are highly scalable. So that's why we want to make use of the unique computing capabilities of the blue water. So the rest of my talk will focus on the DNS methodology, software's workflow, and results of our domain science. To simulate these supersonic turbulent boundary layers, we have a very special challenge to deal with on the choice of this numerical scheme. The numerical scheme has to be very high order and non-dissipative to resolve the turbulence region. But in the same time, In order to capture the shock wave, it has to have the ability to be shock capturing to deal with these high density gradient regions in a supersonic flow. To do that, we have to add dissipation, and this is a conflicting requirement for our numerical schemes. The high density gradient regions can be seen in this figure, which shows Mach 14 turbulent boundary layers. To deal with this challenge, we choose the high-order finite difference method and use a hybrid numerical scheme. To capture the broadband turbulence field, high-order non-dissipative central scheme is used. And to capture the shock waves, the weighted, essentially non-oscillatory scheme is used, which is also called Winnow scheme. And we rely on a shock sensor to distinguish the shock wave from the smooth turbulent regions and apply the corresponding numerical schemes on different regions. And the structure of our DNS code is like this. The solver is first initialized by either uniform flow or similarity resolutions, and we solve the full three-dimensional compressible Navier-Stokes equations, and the convective flux terms are treated by the hybrid schemes I just talked in last page. The viscous flux term is discretized using a fourth order finite difference central scheme. And in terms of the time integration, we use the third order explicit Runge-Kutta method to update the 6 primitive variables. And our code is written in Fortran 2003. It is parallelized in MPI, and we use the parallel HD5 to deal with the I/O part. For the parallel structure, we decompose our three-dimensional computational box only in 2 directions, the stringwise direction and the spanwise direction. So essentially, a Z-pencil is used in each processors. Because we are using a finite difference method, so there is a small overlap region among different processors, and the value of these overlap regions are communicated by the MPI. The black areas here shows overlap regions. The data in these regions are copied from the inner side of its neighboring processors. And we do the profiling of our DNS code. First, we focus on only the computational parts. Here, the computational part includes the discretization of convective flux and viscous flux. And both the strong scaling and weak scaling shows our DNS code is highly scalable, up to at least 32,000 cores. And in terms of the I/O, our DNS code has 2 different I/O requirements. The first one is the restart I/O, which is a snapshot of the whole flow field, and it's written every 1,000 steps. So when one run finishes, we can restart using the latest flow field. The second one is the analysis I/O. It is an ASCII dump of running average statistics and time series in 2D plane cards and 3D subsets. They are used to monitor the convergence of the simulation and for post-processing, such as statistical and spectral analysis and visualization. And for each production run, we also archive all the ASCII data file and time series data file, and we save up to 10 restart files. So we have 2 different implementation for the I/O method. The first one is the so-called the one file mode. Basically, all processors collectively write into the same single file using the parallel HD5. And the second one is the multiple file mode. In this mode, we allow the data file to be written in a small number of different files. So this figure shows how this mode works. For example, if we choose the file number equals to the X partition number, the file will be written out as if it is partitioned in the X direction, and so does the Y direction here. The choice, okay, thank you. The choice between different file modes depends on how many processors we are used. And we do the profiling for the I/O performance, and we find that for the one file mode, it doesn't scale up very well. For example, to write out a single file with 160 gigabytes with 32,000 cores, it will take 30 minutes. However, when we choose to the multiple file mode and set the file number equals to the Y partition number, it takes only 0.1 minutes. So with the fixing of this I/O problem, we test the overall performance of our DNS code. The weak scaling also shows that our code is highly scalable. The bar chart here shows a breakdown of our DNS code. We can see most of the time is spent on the computing part, and the I/O part only takes about 10%. And another thing to mention is our MPI communication time is negligible in our DNS code. So far, I've been talking about the DNS methodology and the workflow, and now I would like to tell something about the results of our domain science. We extend our DNS simulation of the flat plate to an asymmetric nozzle. So the nozzle geometry and flow conditions match those of the Maha 6 Hypersonic rotary tube branch wide. This kind of simulation is beneficial because it allows a direct comparison between numerical data and experimental measurements. And the figure here shows a numerical Schlieren for a snapshot of the flow field. We can see the wavefronts exhibit preferred orientation with respect to the nozzle center line in this streamwise and radius direction with an angle of about 28 to 29 degrees. And one major difference between this nozzle and the flat plate is that the acoustic field comes from all directions instead of one direction in a single flat wall. So the difference can be seen from the pressure fluctuation intensity. We plot the pressure fluctuation intensity along the wall normal directions. This pressure fluctuation intensity reaches a plateau outside of the boundary layer. And the intensity inside the nozzle is higher than that of a flat plate due to the noise reverberation effect. And we further compare the power spectrum density of these two different configurations. A reasonable agreement is seen between these two different configurations, which indicate this reverberation has very little or no effect on the power spectrum density. The structure of the pressure fluctuations is analyzed by the two-point correlation coefficients. So it is plotted along different wall normal heights. All right. Outside the boundary layers, the structure has an inclination angle of 28.5 degrees, which is very close to the wavefront angle. And when it approaches to the nozzle center line, the structure becomes more and more homogeneous. This is because the wave of these pressure fluctuations, it is traveling both upward and downward in this region, and they contribute equal to the formation of these pressure fluctuation structures. And to summarize, we utilize the computational power of this blue water to generate a DNS database of high-speed turbulent boundary layers. And the database is used to study the global pressure fluctuation field. We also make use of the blue water project to scale our DNS code, such as by using the software profiling tool, the parallel I/O, and we are working on this MPI, OpenMP hybrid code. So finally, I want to acknowledge Dr. Milan Chowdhury, one of our collaborations in NASA Langley Research Center, the funding support from Air Force, and the computing resources from NCSA through NSF petascale computing allocations. And thank you all for your attention.